Okay, my thing dropped. My camera dropped. Said it right. Would you all like to turn on your camera so that I can see your faces and your classmates can see your faces to add a human touch? Yeah, thank you, Jonathan. Thank you, Mike.
Before we start, I got a question.
Yes.
So for the homework assignment, well, I had a problem on one of them, and some of the other students said that you answered it in office hours.
Yes.
And I didn't see a lecture posted or the video posted for that or for the lecture on Friday. So I was just seeing if you could send those to us.
Yeah, I can send that. Yeah, I can send the office hour video. Let me make a note on that.
And then the Friday lecture as well, because I didn't see that either.
Friday lecture is not there?
I didn't see it. I don't know if anybody else has.
Okay, let me check again, okay? After the lecture, I'll do that immediately.
Okay, thank you.
Okay. Any other questions? That's a good point. So if you have any issues, it's good to raise these issues with me during lecture hours. Let me see. I'm going to share. Okay. Okay, these are the topics I'm going to cover today. It's on polarization. And first, before I do polarization, I will start with gyrotropic medium, which is a very kind of, a very special kind of medium that is very interesting. But we have enough technical knowledge to address this medium right now. That's why I thought it would be a good time to address it. The algebra is rather complicated, but the physics could be understood quite easily. And after studying gyrotropic medium, we will study wave polarization. So let's study what a gyrotropic medium is. In the gyrotropic medium, what we have is that we have a permittivity number, which actually becomes a permittivity tensor in the gyrotropic medium. And this can be done and demonstrated quite easily with some very simple mathematics. And the place where you experience or see such a medium is when you have a magnetic field B, like the Earth magnetic field. For instance, the Earth B field. And then if you have a wave propagating in the K vector, the wave always propagate with the K vector in Earth magnetic field. And you will see that actually the wave vector gets rotated as it propagates. Okay, and that happens in the ionosphere. You now know that if we have a good Earth, the good Earth has a layer of atmosphere, and up above the atmosphere, the air is rarefied. It's so rarefied that the electron is torn away from the atom, and we have a layer of ionosphere. And as you have learned, ionosphere behave like a plasma. And if we are below the plasma frequency, the radial wave would be reflected by the ionosphere, and the radial wave cannot penetrate. And that's why Marconi was so lucky. He was able to send a signal from England to Canada in the early part of the 20th century, making wireless communication a success. But let's look at gyrotropic medium. Gyrotropic medium is based on Lorentz force law. And you probably have seen this Lorentz force law before. The first term is, of course, Coulomb force that you have learned before. The second term is called the V cross B force, as the mathematics suggests. What it says is that if I have a charge Q moving in this direction with the velocity V, and if I have a magnetic field B pointing in the, say, out of the paper, then V cross B will give me a force that points in that direction. And that will cause the charge Q to gyrate if it goes through a magnetic field. If it goes through a static magnetic field, the charge would gyrate and it will travel in a circle. And the frequency at which it gyrates is called the gyrotron frequency. And you will learn about this frequency in a little while. So we can actually use what we have studied before, which is the frequency domain technique, to solve this problem. First of all, you would assume that B is very simple. Let's assume that B is just pointing in the Z direction without loss of generality. Then let's assume that the wave is, or the charge is having a velocity that only has X component and the Y component. And then we can simplify Lorentz force law by quite a bit. Also, let's assume that the electric field is in the XY plane. Okay, and if we have these assumptions, things will become simpler. And according to Lorentz force law and Newton's law, then mass times acceleration is equal to force. And then I will have the Newton's law together with the Lorentz force law could be written together as such. And I can also write the right-hand side, okay, mass times acceleration is that, but I can also write the right-hand side in terms of the r dt. V is just the r dt cross B, okay, because we know that V is equal to dr dt, which is the definition for velocity. So if we now plug in this simple assumption for the electric field, and then assuming that R is very simple, that R is very simple, so that we would have m omega square R using phasor technique. The left-hand side will become such, and then the right-hand side will become something like, well, Q x e x plus y e y plus, and then using phasor technique, we're going to change the r dt into j omega q r cross with b. Okay, we will have this simplified equation, and let me see what else we can do. With this simplified equation, I can further write the fact that r is equal to x plus y. Again, noting that x hat and y hat are unit vectors. So a position vector can be indicated as such. And then my b is just zb naught. And if you make all these assumptions, then you will see that the equations that you have in the previous slide, which is this one over here. Let me see if I can make it bigger. This equation that you have in the previous slide, the last equation, can be written as minus m omega square x will be equal to And if I assume that the charge Q is minus E, okay, the right-hand side will give me EX plus, and in the second term, if I again assume that the charge is minus E, I would have J omega B0 Y, okay? Because my R has a Y component, and the Y component crossing with a Z, Y cross Z gives you minus X, and that gives you a minus sign. So that turns this into a plus sign. And this is the equation for X component, and you can write down the equation for the Y component as well. And it will turn out to be something like minus E, EY plus J omega B naught X. Okay, so you have two equations and two unknowns. You have two equations, two unknowns. The unknowns are X and Y. And you're assuming that EX is the input. You want to look for a permittivity tensor or some kind of a permittivity chi. So you will have this is an input, and you like to look for what the output is. P is something that is proportional to X and Y, as you have learned when you study the Drude-Lorentz Sommerfeld model, because P is proportional to X and Y because they're dipoles. The dipoles because eventually you will have to multiply the displacement by Q to get the dipole moment and also the dipole polarization density. So we would like to invert this equation to express the output. Output is P, which is this, in terms of the input. And let's assume that B naught is a constant. B naught is a constant because it's just the background static magnetic field. And this equation is not easily solved because it has two equations and two unknowns. And our predecessors figure out a clever way of solving this equation. And the clever way to solve this equation is to define new variables. I define an X plus to be a X plus JY, and then I define X minus to be X minus JY. And you can easily show by very simple algebra that if you add these two equations, like if you multiply the second equation by J, add them up, and then you multiply the second equation by minus J and add them up, you have actually two simplified equations. The two simplified equations will look something like the left-hand side will give you M omega square S plus or minus, depending on how you add them up on the left-hand side. And in the right-hand side, the EX and EY will also be added in a fashion that makes it very simple. And I will call it E plus and E minus. Or let me write it explicitly first. It will be EX plus or minus JEY, depending on how you add these two equations up. And then you would have the other terms, which is also the same as omega B naught. You can actually collect these two terms and add them up together, and then it would be in the manner of X plus and minus, S minus again. So this equation is greatly simplified in the sense that the two inputs are still EX and EY. Instead of defining the inputs as EX and EY, I can define my input to these equations as E plus and E minus. So written in this manner, then this equation becomes greatly simplified, and it will have something that looks like S minus is equal to a constant E divided by M omega square, and then I will have to take this to the left-hand side, okay, because my unknown is s plus and s minus. My input is my ex and ey. And if I take that to the left-hand side, I will get something like omega e b naught, okay? And then my input is this. So you can actually solve this equation very easily to solve for the unknowns in terms of the input. And mathematician calls this a diagonalization procedure. If you're not mathematically inclined, it doesn't matter. It's just a clever way to manipulate two equations and two unknowns into an easily solvable form. Okay, and of course, we have s plus and s minus, which are in terms of x and y, and you can derive the polarization density from that as well. For instance, I can derive px to be nex and so on, because the polarization density in x direction is given by this. And then I can also define p plus or minus to be something like px plus or minus jpy. Because these are just clever mathematical tricks. And if you do that, then what you have is that from this equation, where you can have px and py written in this manner, and then the left-hand side is just x. Okay, the left-hand side is just x, and if you plug in the left-hand side into such a kind of equation, you have finally a simplified equation. Let me see.
Hey, Professor.
Yes.
It doesn't matter a lot because you've gone through most of the derivation, but I think on your second equation near the top, you missed a minus sign. It should be EY minus J omega B naught X.
Oh, you think so?
Well, it's Y cross Z, which is negative X.
Okay. Yeah, you're probably right. Let me just put it in, okay? But the detail is written up in the lecture notes. But thank you for pointing that out anyhow. It shows that some people are paying attention, which is good for me. So if you have this relationship, we finally obtain some very simplified relationship in terms of the polarization current, not polarization current, but the polarization density in this coordinate system, which is NE. This is like displacement. This is like X and Y. This is like your displacements. And then you can write this as being equal to NE C plus or minus a constant. You can write this in terms of, the most important thing is that you can write it in terms of a constant. Okay. And this constant, I can say that it is like the chi, or the polarizability of the medium, or we also call this the susceptibility, if there's a big word for it. But this susceptibility would be expressed in terms of this new coordinate system, would be in terms of x plus jy kind of system. And these are just clever mathematical trick to write this in this manner, and the solution is very simple. However, you can also go backward. Having written things in the the physicists will call this the rotating coordinate system. You can go back to the non-rotating coordinate system, which is p plus p minus over 2. You can easily show that the y component, the Cartesian coordinate system, the p plus and p minus can be converted back into px and py again by using such a trick. Okay, there might be a j involved. Okay, I'm not sure. I can check my more accurate lecture notes. There should be a j here. Okay, to be more precise, you can go and check out the algebra. What it says is that once you find a relationship between P and S rotating coordinate system, you can find the relationship between Px and Py in the Cartesian coordinate system again. And there's a lot of algebra. I will not go through the algebra, but eventually you would obtain that P is equal to epsilon naught chi dot E. Okay, back in the Cartesian coordinate system. And then the chi that you have obtained after some algebra is a tensor. It looks something like, let me see. I have it written out carefully in the lecture notes. Okay, J chi plus minus chi minus, and then I will have a minus J chi plus minus chi minus, and then I will have chi plus chi minus. Okay, the chi that I have here is obtained from here. You know how to derive that chi after some algebra. What it says is that you can find this tensor in closed form. Okay, you can find this tensor in closed form, and once you have this tensor, you can find the permittivity tensor for the entire medium for D. Okay, and then you can find this and you can call this the effective tensor. So this is just a very simple derivation for a gyrotropic medium. And you notice that I did not prove with all the details, but you notice that this tensor is Hermitian. That is, if these are all real numbers, if chi is a real number, you find that this term is the complex conjugate of this term. So such a kind of tensor we call Hermitian. Okay, let me write Hermitian here. Okay, so the thing about such a kind of tensor is that it's rather complicated, but what it tells you is that if you have a wave that is propagating in such a medium, you can break the wave into a right rotating wave or left rotating wave. I would not say it yet at this point. Like if you go back to this equation and look at it again, and what you have is that the wave E, okay, the wave E, any wave polarization can be written as either a sum of E plus and E minus. That is, if you define E plus and E minus to be this quantity over here, okay, and in this coordinate system or in this transformed variable, these equations are very simple. Chi is also very simple. Chi is just a scalar number in the rotating coordinate system. Okay. However, if you express this relationship back in the Cartesian coordinate system, chi becomes very complicated. What it tells you is that if you have a wave, if I have a wave that has, say, EX component and EY component, okay, I can also write this wave in terms of EX plus JEY plus EX minus J. That's not the right way to say it, but this wave can be written in terms of, let me see, EX plus JEY. Yeah, that's not a good way to say it, but let me not say it this way. But this thing can be written in terms of a positive rotating wave plus a negative rotating wave. You can very easily show that given any wave, you can always break into the right rotating component plus the left rotating component. And what it says is that these two components would propagate with a different susceptibility tensor, or in this case is a scalar number, which means that these two waves, these two components would propagate with different velocities. Because they propagate with different velocities, so if you have any polarization, when broken up into these two rotating components, one of these rotating components will rotate or propagate faster than the other components. So if you started out with, say, an electric field that has this kind of X and Y component, after the wave propagates through such a medium, okay, the X and Y component will get altered. The wave will propagate in such a way that the electric field gets rotated. And you can demonstrate this quite easily. And I'm not going to demonstrate the mathematical detail. For those who are mathematically inclined, you can see this right away. Anything can be decomposed into the right rotating wave and the left rotating wave. And because their chi's are different, the effective permittivity will be different, and it will propagate with different phase velocity. And after that short distance of propagation, when you try to add them up again, they don't point in the same direction again as before. This is called Faraday rotation. This happens in the ionosphere. So what happens is that if you have the ionosphere, you send a radio wave up there. If you send a wave that is polarized like this, the wave that goes through the ionosphere might be polarized in a different direction, and that poses a severe problem in satellite communication from the Earth. If you send something from the Earth to the satellite, say if you have a satellite out there, okay, the wave polarization gets rotated, and the way to overcome this problem is to use circular polarization, as we will learn in a little while. Okay, with circular polarization, we overcome this problem. Okay, any questions so far on Faraday rotation? Okay, if not, then we will go about to study wave polarization and how we can define a circularly polarized wave and design an antenna that can give a circularly polarized wave, so that when we send a signal out to the outer atmosphere, the rotation of the wave polarization by the ionosphere does not give us a problem. Okay, so one quick way to study polarization is to actually write out these things explicitly. Let me say that if I have an electric field, I think we already learned very early in the course that in the time domain, I can write the electric field to have the X component behaving like this. Okay, and this is a solution to Maxwell's equation in a free space or vacuum. And by the same token, if I make the electric field polarized in the Y direction, I can write the electric field to be as such. And I'm just writing this as a linear superposition of two fields. So this is X direction, this is Y direction, and the wave is propagating out in the Z direction. Okay, and this you have studied in your course before. In your course, you just study one of these two components, but I'm just adding this as a generalization. But now I want to express this in a time domain to see these effects of polarization. So if I were to write this in the time domain, I would like to write this as E1 cosine of omega t minus beta z, okay, plus y hat E2. Let's assume that E2 is different from E1, and the second term will be cosine of omega t minus beta z plus alpha. So in other words, the y component and the z or the x component are not in phase. Okay, they're out of phase. If alpha is 0, then the x component and the y component are in phase. And for simplicity, we assume a time harmonic signal for both components. Of course, you can have a general signal, but they will be too difficult to analyze. So time harmonic signal is also called CW, okay, monochromatic. It's given different terms depending on which area you come from. So we can now look at this polarization of this wave for when alpha is equal to pi over 2. That is, if they are 90 degrees out of phase with respect to each other. And we can start to plot this wave vector for different t. For simplicity, let's assume that z equal to 0. Okay, if we assume that z equal to 0, then the electric field is just x E1 cosine omega t plus y E2 cosine of omega t plus alpha. Okay, I fix my observation point at z equal to 0 for simplicity so that the equation becomes simpler. And then the second term, because I look at the case where the phase shift is 90 degrees, it just becomes pi over 2. Okay, so let's plot this wave vector as a function of time to gain insight. Okay, so we can plot it for different times, and we can start with t is equal to 0 or omega t being 0. Then if we look at this wave vector when t is equal to 0, then I would have cosine of omega t being 0. This would give me E1. Okay, E1. And so the electric field EX would be E1. And then the y component would be the second component. And if you set t equal to 0, cosine of pi over 2 is 0. So EY is 0. So if I were to plot this thing, it will look something like this, that the x component and the y component, okay, EX and EY, will look something like this with the electric field pointing in the horizontal direction. Okay, now if I make omega t bigger, it's easier to think of it as increasing to pi over 4, which is 45 degrees. And if you look at the omega t being pi over 4, then you cosine of 45 degrees is 1 over square root of 2. Then you will have EX is E1 over root 2. Okay, and then you have EY. EY would be cosine of 45 degrees plus 90 degrees. And this gives you 135 degrees. And if you take that, you will get E2 over root 2. Okay, so it will be something that looks like the y component is negative, the x component is positive. So that electric field would actually start to point in this direction. Okay, this is omega t equal to 0. And then when omega t equal to pi over 4, it starts to point in that direction. And then you can keep going with this exercise. It's a rather simple exercise to do. And if you let omega t is equal to pi over 2, you find that the wave vector points downward. Okay, this is the case when omega t equals pi over 2. Okay, so you get the point. The point is that with these two electric fields, x and y components superposed on top of each other, and that they are 90 degrees apart in phase, then this wave vector would rotate. And in general, it rotates in this direction as a function of time. You can Convince yourself that as time progresses, the wave vector rotates in this manner. Okay, the wave vector rotates in a manner that if you were to put your thumb in the direction of propagation, the direction of propagation is z. Okay, if you put your thumb in the z direction and your fingers in the direction of rotation of the electric field vector, this polarization is called a left-hand polarization. And because the shape that it traces out is an ellipse, is not a circle, this is called a left-hand elliptically polarized wave. Okay, LHEP. Okay, so if, however, E1 equals E2, then you get left-hand circularly polarized wave. Okay, and then, however, if the phase alpha is minus pi over 2 instead of plus pi over 2, like here we put in a plus pi over 2. If you make alpha minus pi over 2, you will go through the exercise and show that in this case, the polarization is right-hand elliptically polarized. And then if E1 over E2 equals 1, then you will have right-hand circularly polarized wave. So it is quite easy to understand. The physics is rather simple. The only thing is that you just have to remember all these things. I usually don't remember them myself. You have to put your thumb in the right direction, put your finger in the right direction. You can figure out the polarizations of these different waves. Okay, are there any questions regarding different kinds of polarization? Actually, I have a nice picture here, which shows this different kinds of polarization. And what you have is that this is how the wave vector will rotate as a function of time. And then you can change the relative ratio of E2 over E1, when the ratio of E2 over E1, when they're 90 degrees apart, when this phase is 90 degrees apart, we show the phase of 90 degrees apart in this direction, you get a circular polarization. And then if it's in the opposite sign, you get a circular polarization of the right-hand polarity, but all these are to be left-hand polarity, left-hand circularly polarized, and left-hand elliptically polarized wave. And those that are in the upper half plane will be right-hand circularly polarized or right-hand elliptically polarized, depending on the ratio of the two amplitudes. Okay, you have this polarization chart in your lecture notes as well. So are there any questions so far? And then there is something called the axial ratio, which I will not go through in the lecture because it's rather laborious. You can see that it's all mathematics from this point onward. That is, the ellipse is not necessarily horizontal or vertical like at these 4 points here. The ellipse can be tilted at an angle. Okay, and the mathematics of that is kind of complicated. You can actually find the tilt angle by going through some algebra or working with elliptical coordinate system and so on. I will not go to that. I have that documented in the lecture notes. You can find this angle theta. And there's another thing called the axial ratio. The axial ratio is the ratio of the major axis to the minor axis of the ellipse. Okay, it is also used very much in antenna technology. If you are in wireless communication and designing antennas, you will have to talk about axial ratios, and you like to have A and B to be equal to each other. So A and B is good axial ratio. Then the axial ratio is 1. Okay, this is the figure for deriving that, and the concept is not deep. The concept is rather straightforward, but the algebra that you have to be involved with in deriving this is rather complicated. Okay, so let's move on to something else then. Let's move on to polarization and power flow. We have learned about power flow two ways. One in the time domain using instantaneous Poynting theorem. Another way is to use complex Poynting theorem. And we studied this first using both ways, okay? So first with instantaneous and then later on with complex Poynting vector, okay? So let's begin with Poynting theorem. And you know that the Poynting vector there is just E in the time domain crossing with the H in the time domain. Okay, we have already written this down for E, and then if we were to take the instantaneous electric field and fill in these formulas, what we have is that, let me see. What we can show is that the electric field, as we said before, is X polarized. For this very simple example, we will just use X polarized electric field. And then the magnetic field, because it is a TEM wave, you can derive the magnetic field quite easily. It will be the electric field divided by eta. Eta is the intrinsic impedance of space. And then the magnetic field will be in phase with the electric field. And if you were to now plug this into the above, you will find that the instantaneous Poynting vector is just the cross product of these two, and it will be something pointing in the z direction. S cross y give you z, and then if you multiply the two together, you will get E naught squared over eta cosine square omega t minus beta z. And what you see is something traveling through space. And if you envision this through space, it's a cos square function propagating through space. So a cos square function looks something like this. Okay, so I'm just plotting the Poynting vector as a function of t and z. So what you see is a lump of energy propagating through space. That is when you have a traveling wave. This we know is a traveling wave. And for the traveling wave case, the Poynting vector looks something like that. But for the circular polarization, this is actually an arbitrary linear polarization. This we call the linear polarization. I don't know if I mentioned that before or not. That if you only have the X component of the electric field, you have something called the X polarization. Or if you have X and Y component to be in phase, you also have a linear polarization. Then the electric field will be tilted at different angles. You can go through this exercise yourself. So what we have here is actually a linear polarization case where the electric field is pointing entirely in the X direction. But we can do something more interesting. Let's assume that the electric field now has both X and Y polarization, and it's a lot easier to do the math in the frequency domain. So I will assume that we have a frequency domain representation of this. And in terms of phasors, phasors do not have time dependence now. And the general polarization can be written as this in the frequency domain. Okay, so what we have then is that if we were to look for the case of a left-hand elliptically polarized wave, that is the case where E1 and E2 are 90 degrees out of phase, but not necessarily of the same amplitude. Then the phasor representation for this field is that you have this in phase, and then you have a relationship between them. Okay, X E1 plus Y E2. And then they could be 90 degrees out of phase. So alpha would be pi over 2. And if alpha is pi over 2, then I would just have a J here. Okay, so if I write this in the phasor domain, the electric field is something of this sort. And we have not done this before because when we were deriving this, we actually were writing things in the time domain. So it will be refreshing for you to see them in the frequency domain again. So if you have left-hand circularly polarized wave, that is when E1 and E2 are equal to each other, then in the frequency domain, they will look something like this. Okay, so left-hand elliptically polarized wave and left-hand circularly polarized wave. Then it is time for us to find the Poynting's vector, complex Poynting's vector. Okay, so we can do one of this, and the H field would be something of the form of curl of E over J omega mu, okay, with a minus sign. But then if we assume that J beta is pointing in the Z direction, okay, the beta vector or the propagation vector is pointing in that direction, then this equation simplifies to beta cross E over omega mu. Okay, beta cross E over omega mu. And you can figure out what the magnetic field is, for instance, for this polarization, which is circular polarized wave. The H would be just equal to, depending on your choice of plus or minus, if you have like a left-hand circularly polarized or left-hand circularly elliptically polarized or right-hand circularly polarized or right-hand elliptically polarized, then your H field will be something like X minus JY. Okay. J E naught over eta, E to the minus J beta Z. Okay. You can show this quite easily by going through the algebra. I will not go through the algebra, but you plug it in here, and we're just taking one of the left-hand circularly polarized case, and I find this to be my H field. And if you do that, then yeah, I hate this, but I have to cut them one by one. I don't know how to cut them in total. Okay, but what happens then is that I can figure out my H field and then look for the E cross H. And what I have is that I don't have time to work out the detail, but what happens is that for the circularly polarized wave, you can show that the Poynting vector is actually a constant independent of time. Okay, constant independent of time. which means that if you have a circularly polarized wave, instead of having energy travel in the lump like this, the energy that it carries actually would be a constant. And that's peculiarity of a circularly polarized wave. Okay, I will let you go unless you have any questions. Do you have any questions? The detailed derivation of the last part is done in the lecture notes. Okay, as to how you find that pointing vector. You find that it actually turns out to be a constant. You go to the algebra and do all this algebra, E cross H turns out to be a constant. Okay, and it's done in the lecture note. Any questions before I stop? Hello?
Homework 3 been released?
What is the question again?
It's about homework 3. Has it been released?
I sent it out last Friday. Did any one of you get it?
Oh, I might have missed it.
Yeah. I think I did, but let me check.
Yeah, I did. I got it.
Yeah, some students got it. Maybe you check your mailbox, you will find it.
Okay, sure.
Okay, so it has been released. At least some students got it.
Yeah,
Okay,
I will upload it to Brightspace.
You put it in Brightspace, right, Ivan?
Yeah, I will upload it to the Brightspace so
Okay, good.
everyone has access.
Okay, good. Ivan will make sure that it's up there on Brightspace. Any other questions? If not, I'll let you go and you keep safe out there. And take good care of yourself. And I see you on Wednesday. Okay? Take good care. Bye-bye.
Thanks, Professor.
And tomorrow there will be an office hour. Wednesday night there will be an office hour. And Thursday night there will be an office hour. Okay, if you have any questions. Yes?
I do have one question. Are you going to upload solutions so that we can like look at the homework and make sure we understand what we did right and wrong?
Oh, sure. I will ask the TAs to do that. Ivan, can you make sure that the solutions are uploaded?
Yeah, I don't have solutions, but if you provide me with, I will upload
I think
them.
Jay has a solution. We can ask Jay for them and then
Sure.
make sure they're uploaded. Okay?
Awesome. Thank you so much.
I'll talk to you later. Okay, bye-bye.